Okay, this video is the beginning of hypothesis testing, a very important idea that we're going to explore in lots of different situations. But here's the introduction. We are surrounded by data, and we see it in the news with all these facts that come up. And here are some examples of things that we know now because of statistics and hypothesis testing. These headlines are all results of experiments that were done where there was a parameter that was tested statistically, and the conclusions led them to make these bold statements. So here's the process of the test. You begin by making an assumption about a parameter. This assumption is called the null hypothesis. The parameters that we have looked at so far are the population mean, mu, and population proportion, p. You'll learn more tests about more parameters next term as well. So you make an assumption that the parameter equals a certain number. Then you go out and collect your data. So you actually have a sample of observations, and you collect either a sample mean or sample proportion or some other statistic. And you look at your results and you use probability theory to decide whether they were likely or unlikely. If they were very unlikely, then that is evidence to reject the null hypothesis. And if you reject, that means that you have statistically proven that the parameter couldn't be equal to the number that you originally assumed. So here's an example that demonstrates the logic. Let's say we have a coin and we want to test whether it's fair or not. So we're going to begin by assuming the coin is fair, that the probability of heads is 0.5. Then we're going to flip the coin 100 times. These coin flips are our sample of observations. If we get 90 heads, then that would be an extremely unlikely outcome if the coin were really fair. It is so unlikely that it is simply unbelievable for the coin to be fair, and it statistically proves that the coin is not fair, that the probability of heads is not 0.5. Another way of saying it is that we don't believe that 90 heads is realistic just by luck alone. So something must be wrong with the coin. If, on the other hand, you got 55 heads, well, this isn't exactly the 50 heads that we would expect of a fair coin, but it's certainly well within reason for 100 flips of a fair coin. The probability of getting this kind of outcome is pretty high. So there's no real reason to doubt the assumption that the coin is fair. Or, in other words, we can easily believe that this result is simply due to random luck, and we have no strong evidence that the coin is unfair. Some people would say that this proves the coin is fair, but that's not quite right either. It simply does not prove that the coin is unfair. There's a subtle but important difference between those two statements. So we've established that 90 heads is unbelievable and 55 heads is reasonable for a fair coin. Somewhere in between these numbers is a threshold where reasonably unlikely becomes too unlikely to believe. This threshold is called the critical value. It is the cutoff point that determines whether or not you decide to reject the null hypothesis. What do you think that threshold is for the coin example? 60 heads? 65 heads? 70 heads? Eventually, you would reach a point where you would have to say enough is enough. It is too unlikely to believe that a fair coin could do that. There are actually three factors that determine where the critical value is. The first is the hypothesis. And as we shall see, there are three kinds of them. There are hypotheses where you reject if the outcome is too large. There are hypotheses that reject if the outcome is too small. And there are hypotheses that reject if the outcome is either too big or too small. We'll look at these three varieties very soon. The second factor is the distribution of the statistic. We've already seen two common distributions so far, the z and the t distributions, but you'll study more in the next term too. And the third factor is the probability threshold that defines what is considered too unlikely. This threshold is called the level of the test. You can choose for yourself what you feel should be the level, although it is common practice to use 5%. But a more demanding person might choose 1% as the level. Either way, the level is chosen so that if your sample data is so unlikely that its probability is less than the level, then you would reject the null hypothesis because it's too unlikely to believe. So let's actually do an example about TIE IQ scores. We have known SD, so this is a z distribution. We are testing if the mean is greater than 100, so we will assume in the null hypothesis that the mean is equal to 100 and only reject if the sample mean is significantly larger than that. This is called a one-tailed hypothesis because we only reject if the sample mean is too large. So the distribution looks like this, under the assumption that the mean is equal to 100. Then there is a critical value k such that if the sample mean is larger than k, then we will reject the null hypothesis. Since the level of the test was given as 1%, then the area beyond k is 0.01. If there's 1% area in the right tail of the z distribution, then you should remember that z is equal to 2.326. And this is the formula for z for the sample mean, if the SD is known. And we're going to plug in all the numbers given in the question and solve for x bar. And mu is in the null hypothesis as 100, and the SD and sample size are given in the question. Since you would reject if z was greater than 2.326, that means you would similarly reject if x bar was greater than 106.978. So the critical value that I called k in the previous slide, the threshold for rejecting the null hypothesis, is 106.978. And if the sample mean was greater than this number, then we would conclude that the mean IQ of all TIE children is significantly greater than 100. Okay, what would happen if we change the level to 10%? Let me first say that virtually nobody would realistically choose 10% as their level. It's just too large. Most people wouldn't consider that probability small enough to conclusively prove anything. Anyway, the distribution again looks like this, and again we would reject the null hypothesis if the sample mean were larger than some critical value k. But this time the area beyond k is 0.1 or 10%. In the z distribution, 0.1 area in the right tail means that z is equal to 1.282. Plug in all the same numbers from before, and you'll see that the critical value is 103.846. This is a lower threshold than before. So increasing the level from 1% to 10% actually means that we need less demanding evidence in order to make the decision to reject the null hypothesis. Okay, same question, but this time we're told that the level is 5%, and I want the sample size such that the critical value is equal to 101. This is a new twist on the question. Once again, the distribution looks like this under the assumption of the null hypothesis that the mean is equal to 100. The threshold for rejection is 101, and the level is 5%, so the area beyond 101 must be equal to 0.05. In the z distribution, 5% area in the right tail means that z is equal to 1.645. Create z by subtracting the mean and dividing by the SD, and then set it equal to 1.645. And solve for n. You should get 609 people as the required sample size. Okay, new question, the stopping distance for a car. We have a known SD, so we have the z distribution, and this time we're testing to see if the stopping distance is less than 30. So we're going to assume that the distance is equal to 30, the null hypothesis. And we're only going to reject if the sample mean is significantly smaller than 30 or less than 30. This is a one-tailed left tail test. The distribution looks like this. The mean is assumed to be 30, and there is some critical value k such that if the sample mean is less than k, we will reject the null hypothesis. Since the level is 5%, the area beyond k must be 0.05. For the z distribution, an area of 0.05 in the left tail means that z is equal to negative 1.645. It's negative because it's in the left tail. Plug the numbers into the formula for z. Mu is again given in the null hypothesis as 30, and solve for x bar. We would reject if z is less than negative 1.645, which is equivalent to x bar being below 29.42. So the critical value k is 29.42. And if the sample mean were below 29.42, then we would conclude that the mean stopping distance of all cars is less than 30 meters. Okay, this is the last example about SAT scores. We have known SD, so we have the z distribution again. We're going to test whether or not the mean is equal to 500. And we will reject if the sample mean is too big or too small. This is called a two-tailed hypothesis. The distribution looks like this under the assumption that the mean is equal to 500. In this question, we're told what the critical values are. We would reject if the sample mean is greater than 506 or less than 496. And we're told to find the level of the test. The level is the probability of rejection, or the area beyond the critical values. Notice that the critical values are not symmetrical around the mean. That's not a requirement. We just need to find the areas in both tails and add them up. Just be careful that when you subtract the mean to find z, that you remember that we are assuming that the mean is 500 in the null hypothesis. So we get these two z values. If you look them up in your z table, then you'll see that the areas add up to 0.0967, or approximately 10% level. Okay, this is an important introduction to the ideas of hypothesis testing. The next video is about a related concept called p-value, also very important. You have 3 questions now to take care of. Good luck with that, and check out the next video.